and welcome to the second session of AI-900, Microsoft Azure AI Fundamentals. I hope you had the chance to watch the previous video and start building your foundation in AI. I'm Alexandra, Senior Technical Trainer in Data and AI, an AI course lead at Microsoft. Before we dive in, let me share a little about myself. I've been teaching technology for over 10 years, helping learners and organizations embrace innovation. And here are a few fun facts. I have been dancing tango for a decade, I speak 5 languages fluently, and I have traveled to more than 50 countries. In this session, we'll focus on machine learning, one of the core pillars of AI. We'll learn what machine learning is, the different types of learning approaches, and how models are trained and evaluated. We'll also introduce deep learning, explain how it differs from traditional machine learning, and explore how Azure Machine Learning and automated machine learning can help you build and deploy models quickly and efficiently. In this second session, we'll dive into the fundamentals of machine learning, the technology that powers most of AI solutions today. We'll focus on 2 big topics. First, we'll introduce the core concept of machine learning. Then we'll explore how to get started with machine learning in Microsoft Azure. So what exactly is machine learning? At its core, machine learning is about teaching software to make predictions. A machine learning model is essentially a function that calculates an unknown output based on known inputs. The process of creating that function is called training. Once trained, the model can make predictions, a process called inferencing. To understand this better, let's talk about features and labels. Features are the measurable attributes or characteristics of the data, the inputs we know. Labels are the values we want to predict, the output. In mathematical terms, features are often represented as X and labels as Y. So the model learns a function f of x equals y. After training, when we input new x value, the model predicts y, often shown as y hat. Imagine you want to predict how many ice creams will be sold tomorrow. The features could include temperature, rainfall, and wind speed. These are the inputs. The label is the number of ice creams sold, the output. By analyzing past data, the model learns the relationship between weather conditions and ice cream sales. Then, when you provide tomorrow's weather forecast, the model predicts the expected sales. Or another example, if we want to predict the price of a house, the features might include square footage, number of bedrooms, and location. The label is the price. Once trained, the model can predict the price of a new house based on those features. Machine learning comes in different types, and understanding this is key to choosing the right approach for your problem. The most common type is supervised learning. In supervised learning, the training data includes both features, the input we know, and labels, the outputs we want to predict. The model learns the relationship between them so it can predict labels for new data. Imagine you work in retail and want to forecast monthly revenue. The features could include advertising spend, seasonal trends, and store foot traffic, while the label is total sales. By analyzing historical data, the model learns how these factors influence revenue and predicts future performance. Supervised learning includes 2 main approaches: regression and classification. Regression predicts numeric values. For instance, as we mentioned before, predicting the number of ice creams sold based on temperature and rainfall. Another example is estimating fuel efficiency based on engine size and weight, or forecasting monthly sales based on advertising spend. Classification predicts categories. Binary classification predicts yes or no outcomes, like whether a patient is at risk of diabetes or whether a customer will default on a loan. Multi-class classification predicts one of several classes, such as identifying the species of a penguin, Adelie, Gentoo, or chinstrap, or determining the genre of a movie, comedy, horror, or science fiction. Now, let's look at unsupervised learning. This type uses data without labels. The most common technique is clustering, which groups similar observations based on shared characteristics. For example, a retailer might use clustering to segment customers into groups based on purchasing behavior, frequent buyers, seasonal shoppers, or high-value customers. Another example is grouping flowers by size and number of petals, or organizing news article by topic without knowing the categories in advance. Clustering is often used as a first step to discover patterns in data before applying other techniques. Training a machine learning model is an iterative process, and it involves several key steps. Let's break them down and make them real with an example. Predicting house price. First, we split the data into two sets, a training set and a validation set. The training set is used to teach the model, and the validation set is held back to test how well the model performs on data it hasn't seen before. For example, if we have 10,000 houses records, we might use 8,000 for training and 2,000 for validation. Next, we apply an algorithm to fit the training data to a model. This means the algorithm looks for patterns in the training data, how features like square footage, number of bedrooms, and location related to the label, which is the price. Once the algorithm has learned these patterns, we have a trained model that encapsulates the relationships in the data. Think of it as a formula that predicts houses priced based on the features. Then, we use the model to generate prediction from the validation data. We fit in the features from the validation set, like the size and location of a house, and the model predicts the price. Now comes the critical part: evaluation. We compare the predicted price to the actual prices using metrics like mean absolute error or root mean squared error. If it's a classification problem, we will use metrics like accuracy, precision, and recall. For unsupervised learning, where there are no labels, we measure how well the clusters are separated using metrics like silhouette score. Finally, we repeat the process. We adjust parameters, try different algorithms, and keep refining until the model performs well enough for real-world use. Imagine this cycle applied to predicting ice cream sales. We start with historical weather and sales data, train the model, test it, and tweak it until it predicts tomorrow's sales with confidence. Different algorithms are used for different machine learning tasks. For numeric prediction, one of the simplest and most common algorithms is linear regression. It works by finding the best fitting line through data points so we can predict values like house prices or ice cream sales. For classification tasks, we often use logistic regression. Despite its name, this algorithm predicts categories, such as whether a customer will default on a loan or whether an email is spam. For unsupervised learning, key means clustering is widely used. It groups similar data points into clusters. For example, segmenting customer based on purchasing behavior or grouping flowers by size and numbers of petals. Now, how do we know if model is good? That is where evaluation metrics come in. For regression, we measure how far of our predictions are from actual values. Mean absolute error tells us the average difference between predicted and actual values. Mean squared error does the same but squares the difference, making a large error stand out. Root mean squared error takes the square root of MSE, so the error is expressed in the same units as prediction, like dollars for house prices. R-squared shows how much of the variation in the data our model explains. A higher R-squared means a better fit. For classification, we look at accuracy, which is the proportion of corrected predictions overall. Precision measures how many of the positive predictions were actually correct, while recall measures how many actual positive cases we correctly identified. The F1 score combines precision and recall into a single metric to give a balanced view of performance. Imagine a spam detection model. High precision means most emails flagged as spam really are spam, while high recall means we catching almost all spam emails. For clustering, since there are no labels, we measure how well the data is separated into groups. The silhouette score ranges from -1 to 1 and shows how distinct the clusters are. We also look at the distance between cluster centers and how tightly data points group around those centers. A good clustering model creates well-separated, compact clusters that make sense for the problem you're solving. Deep learning takes machine learning further by using artificial neural networks, layers of interconnected nodes that mimic the way the human brain works. Think about how our brain processes information. Biological neurons receive signals, combine them, and pass them on if the signal is strong enough. Artificial neural networks work in a similar way. Each artificial neuron takes input value, applies weights, sums them up, and passes the results through an activation function to decide whether to fire to the next layer. These networks are organized into layers. An input layer that receives a feature, one or more hidden layers that transform the data, and an output layer that produces the prediction. This architecture allows deep learning models to handle complex tasks like image recognition, speech processing, and natural language understanding. For example, imagine classifying penguin species based on measurements like bill lengths, bill depths, flipper lengths, and weight. The input layer receives these measurements. The data flows through multiple hidden layers, where each neuron applies weights and activation functions. Finally, the output layers produces probabilities for each species: ugly, gentle, or chinstrap. If the output probabilities are 0.2, 0.7, 0.1, the model predicts the second one. 0.7 Gen 2 because it has the highest probability. Now let's talk about loss. The difference between the predicted probabilities and the actual label, whether it's 0 or 1, is called the loss. During training, the model adjusts its weights to minimize this loss. This process happens iteratively using algorithms like gradient descent. Each iteration reduces the error a little more, improving the model's accuracy over time. In short, deep learning is powerful because it can learn complex patterns by stacking layers of neurons, just like our brain processes information, but at scale and speed that humans can't match. Now, let's see a quick demo of how this works in practice. If you want to follow the demo, I highly recommend to go to Microsoft Learn, which will have this demo scenario, so you can also do it on your own. In this demo, we will explore together applications that use machine learning to predict unknown values. So we will have 3 different examples. We will start with the home rentals prediction. Let's say I decide to rent my apartment and I need to determine an appropriate monthly rental amount that I can charge the tenant. So for it, I will use the postal code location, property size, and the number of the bedrooms to predict monthly rent price. I can also check the sample data that I use to build this machine learning model, as well as on the right I can check the model details information, the algorithm that we use, its multiple linear regression features that are associated with this model performance metrics that are very important. We have 4 associated to this model. And last not least, there is training data. It represents 70% of the data, and test data that is 30%. It's very normal split that we have 70% in training and 30% in the test. So I can play with this model. I can modify also number of bedrooms, and you'll see that the price will change. The second example that I want to share with you, it's read seed identifier, where we are doing classification with machine learning. So the idea here, by using 3 different criteria, seed lengths, seed widths, and groove lengths, to predict the species of our wheat grains. I can modify them, hit predict, and we'll see the probability that it's comma wheat with 93%. 93% here, it's our confidence score of the model that this is the right wheat that we predict. If I change my seed information, the prediction is changing accordingly, and also you notice that the confidence score will be different. We can check also the data associated with this model, things, seed lengths, seed widths, groove lengths, as well as the model detail. We can check that it was logistic regressions that we use. Information about data set, training, validation, and total amount of rows. For sure, in real life, those numbers will be much bigger. Here are just example. Usually you'll have millions and millions of rows that you use to build your model. And again, the split between training and test. Performance metrics are very important. Accuracy is the proportion of all seeds correctly classified. Precision, it's all about the seeds predicted as a certain type, how many are truly the type. Recall, it's of all the seeds that are actually belong to this type, how many is the model correctly identifying. And F1 score, it's a balance between precision and recall. And the third example here, it's customer segmentation. Let's say we want to do unsupervised machine learning, and we would like to help predict at retail business how to group customers into segments. And here, by using clustering and our customers' information, we created 4 different clusters of our data that we can check in this quarter plot. And we see that our 3 or 4 clusters are actually very well organized. And with it, we saw 3 different parts of demo, in which one using machine learning to build our models and analytics. We saw home rentals, classification, and also clustering. I hope you enjoyed this demo. Let's come back to our presentation. In this second part, we will see how machine learning works in Azure. Microsoft Azure Machine Learning is a cloud-based service that manages the entire machine learning lifecycle, from start to finish. It's designed to help data scientists, developers, and business teams build, train, deploy, and monitor machine learning models at scale. With Azure Machine Learning, you can explore and prepare your data, train and evaluate models, register and manage those models, and deploy them into production for real-world use. It also includes tools to apply responsible AI principles, ensuring your models are fair, transparent, and secure. The main interface for working with Azure Machine Learning is Azure Machine Learning Studio. This is a browser-based portal where you can manage everything in one place. In the studio, you can run code in notebooks, create automated workflows called pipelines, and use visual tools to simplify complex tasks. You can also access automated machine learning, which we'll talk about shortly, and view detailed evaluation metrics for your models. Think of Azure Machine Learning Studio as your command center for AI development. Whether you're building a simple regression model or deploying a deep learning solution for image recognition. Automated machine learning, or AutoML, in Azure Machine Learning makes building models faster and easier. Instead of manually choosing algorithms and tuning parameters, automated machine learning does the heavy lifting for you. Here, how it works. You connect your data, define your prediction goals, whether it's regression, classification, forecasting, computer vision, or natural language processing, and automated machine learning automatically tests multiple algorithms, selects the best one, and optimizes it for accuracy. For example, if you want to predict customer churn, automated machine learning will try different classification algorithms, compare their performance, and recommend the best model. If you're forecasting sales, it will test time series models and pick up the one that gives the most accurate predictions. This approach saves time and ensures you get the high-performing model without needing deep expertise in machine learning. And the best part? You can deploy the resulting model directly from Azure Machine Learning Studio with just a few clicks. Now, let's see automated machine learning in action. So if you want, you can also follow this demo scenario on Microsoft Learn. In this demo, we will discover how to use the automated machine learning to train and evaluate a machine learning model. After that, we will deploy and test it. So here in this example, I'm using machine learning lab environment, in which one first I will need to create a workspace for this demo. If you want to use for the same task Azure Machine Learning Studio, you will need to create first a hub. To do so, in my case, as I'm using Machine Learning Lab, I can create straight away a workspace. I will call it Automated Machine Learning. As soon as I created a workspace, I can open it and starting by adding here my data. So in the Automated Machine Learning, I will create a new job. I will provide this job a name. Let's call it ice cream machine learning, because in this scenario we will predict the amount of ice cream that we can sell over the time. And the data set that I will use, it will be CSV file with the data regarding ice cream sales over the time. So you see there are 200 rows, 6 columns, and information about day of the week, months, temperature, rainfall, and the amount of ice cream that I sold out those days. And in the next steps, I can also parameter, first of all, that my target column that I want to figure out its amount of ice cream to sell. And after that, I can configure my primary metric. If I want to, can also add some additional algorithms here and also change my featureization settings if I want so, just to know what I use as categories. And just save it here and close. In our limits, we can add our metric scores. So first one will stop the training when this metric score is reached. And second, it's experiment timeout. I will put 15 minutes here. For the compute part, we will use server slice, the recommended one. We can review and submit. You see it's running and now it's completed. If we look in the bottom part, we can see the status. And also we could check the algorithm and the model results with the score that it's quite high, close to 1, so it's a very good result. Also nice, we don't have any missing data. And there are some recommendations as well as logs related to these jobs that we can review. There are 74 logs as well. There are some child jobs that were completed. So far so good. Here you see that the best model results are available and the status is complete. We can now register this model, or we can also check the algorithms that we use and deploy it to our environment. So let's hit deploy. We'll select virtual machines that we want to use to deploy, select endpoint name and deployment name, and deploy this model. After it's deployed, we can see the results in our endpoint section. The model is available here as well as endpoint to access it. And very important, we can test now our model to verify that it's working correctly. To test it, we can change input JSON file with data and saying here on Wednesday, June, with those information about rain and temperature, we can check how many ice creams we are potentially selling. So it means that if the temperature and rain information is the following, I could sell 121 ice cream this day. And then in the consume part, we can download this model if we want to integrate it in our own application and use Python code. So here we do have an example of Python code to integrate the following model, where we start with importing the library, downloading the model, preparing the sample data that we can use to replace with our own parameters, and this model is fully available to us. Also, we can do a classification job here to classify the penguins. We discussed this example before. In this case, the task type will be not regression, but classification. This time, as well as I will need a different data set to perform it. Let's call it penguins data. Select CSV data store locally with 344 rows. Again, in real life scenario, you will have much more data there. and we can find the information about each penguin class and the data attached to it. As we did before, we'll decide on the target on the next step. So we won't predict species, it's why it will be our target column. We could parameter some additional algorithms and metrics. We could modify featurization settings, and very important, set up the metric score here, based on which one we want to stop our training. And compute power, review, create, and again here we'll use the logistic algorithm. We can register the models that we want, but this time the task was different. It was classification, and also there are a few information saying that we are missing a bit of data. So if we want to improve this model, we will need to add this data, and also we do see this part in our recommendation. We can review the algorithm from this part and deploy this model by selecting virtual machine and endpoint name. And as soon as it's deployed, we'll find it in our endpoints. A very simple step, again, on the top, deploy. As I hit it twice, you see it was deployed twice, and it's active. And if I want, I can test my endpoint here by providing data about penguins. So I provide some data with the lengths, depths of our penguin and its body mass, and it's saying that it's the first class of my penguin. So we saw together how we can use machine learning lab to make regression and classification methods with our machine learning algorithms. Let's come back to our presentation. In this section, we learn what machine learning is, the different types, how models are trained and evaluated, and what deep learning is. We also explored Azure Machine Learning and automated machine learning. Thank you for your time. This concludes our session. To continue your learning journey, check out other videos in this course or explore Microsoft Learn for more resources. Thank you for your time and happy learning!